Okay, so we're going to look a little bit more into the Pythagorean identity, which is very closely related to the Pythagorean theorem. But what it says is that the sine squared of any angle plus the cosine squared of that same angle equals 1. So we could, on our calculator, just to exemplify this, show that the sine of 15 squared plus the cosine of that same 15 squared is always going to be 1. And you could plug in any number you want and it will always be 1. Now the first order of business here is to prove why, and the proof is going to lie in the Pythagorean theorem. I labeled the hypotenuse C, and so right now we know that a squared plus b squared equals c squared. That's what our Pythagorean theorem tells us. We also know, talking about the sine of alpha, we know that the sine of alpha is opposite over hypotenuse. And the cosine of alpha, because we mentioned cosine over here, is the same thing as adjacent over hypotenuse. So to prove this, we're just going to simplify and manipulate just this left side until we can show that it equals 1. And it's going to happen by substitution. So I'm going to, for the sine of alpha, I'm going to plug in a over c, and that's getting squared. And for the cosine of alpha, I'm going to plug in b over c, and that gets squared. And then when you square a fraction, you square the numerator and denominator. So square both those out. And then this actually can be added already because we have the common denominators. You get a squared plus b squared all over c squared. And then comes in our Pythagorean theorem. So we use SOHCAHTOA, and we're about to substitute out the a squared plus b squared and replace it with c squared right here. So we get c squared over c squared equals 1 equals 1. And there's your proof. Okay, everything in trig always seems to come back to the Pythagorean theorem, and the SOHCAHTOA in this here is no different. So a couple of things, skills we've already been able to do. We could draw this like we would have the past few days. We have an angle lying in Q3, drop the triangle, your cosine, which is adjacent over hypotenuse, gives us this. The Pythagorean theorem gives us negative 15 for that. Find the value of sine, so the sine will equal opposite over hypotenuse. So in that process of getting that answer, obviously we use SOHCAHTOA to label our sides, and we use the Pythagorean theorem and SOHCAHTOA again. With the Pythagorean identity, just knowing this equation allows us to do is to just, if you know that the cosine is negative 8 over 17, plug it in. And then you can just solve for sine. So if this is 64 over 289, so if I subtract 64 over 289 from both sides, I get the sine squared of x equals, now this is 289 over 289, minus 64 over 289 gives you 225 over 289. Square root of both sides, and so you'll know that your sine of x equals plus or minus 15 over 17. Now, because we're in quadrant 3, all students take only tangent is positive, so then we must take only the negative version. So our sine is negative 15 over 17. You know, I honestly think that this is the better way because it gives you that visual, but I think it's helpful to see that both methods work. I'm going to do this one only using the Pythagorean identity since that's what we're working on. So the sine squared plus cosine squared equals 1. So if the sine is 4/5, that's 16 over 25. So if I subtract 16/25 from both sides, I get cosine squared of an angle, I'll just say x. And this is 25/25 minus 16/25 leaves us with 9/25. Square root both sides, so the cosine of x equals plus or minus 3/5. Depending on the quadrant, and we unfortunately aren't given enough information. All we know is that sine is positive. So it has to be in one of these two angles, or quadrants rather. If it's in the first quadrant, it would be a positive 3/5. If it was in the second quadrant, it would be a negative 3/5 for the cosine, which is why when they phrase the question, they say the possible cosine values, because they haven't given us enough information to know whether or not it's the plus or minus, so these are the two possibilities. Okay, on the back side, we just have very straightforward. You'd obviously have your calculator, but why would you use it? This just equals 1. That's our property. What I think they could do on a Regents is kind of give you sine squared of 5x minus 2y plus cosine squared of 5x minus 2y and ask you to do that. Now, your calculator is not going to help you with this. You just have to know that this equals 1. Since we're taking the sine squared and the cosine squared of the same angle, and we're adding them together, that's just our sine squared of something plus cosine squared of something equals 1. In the next exercise, point P is 1 unit away from the origin in Q1, so 1 unit away really always gives you the hypotenuse, so whether it's 2 units away or 3 units away. But this is 1, and this is point P. And this is telling us that sine squared is a half. So if it wants the coordinates, we have to remember that the coordinates are r cosine and r sine. So we don't know sine, but we know sine squared, and we can pretty easily find sine just by square rooting both sides. Square root of 1 over the square root of 2, and then this rationalizes into root 2 over 2. That's just by multiplying by root 2 over itself to rationalize. So this y coordinate is 1 times root 2 over 2, which is just root 2 over 2. To find the cosine, you could, honestly, you could just, if you know your y coordinates root 2 over 2, you could label this root 2 over 2 and then do your Pythagorean theorem. Or the idea here, since we're talking about the Pythagorean identity, is to go this direction. Plus cosine squared of theta equals 1. Now you know sine squared is a half. Solve for cosine squared by subtracting your 1/2 from both sides. And cosine squared of theta equals a half. Square root both sides, and you're going to get your cosine of theta equals the square root of 1, which is 1, over the square root of 2. And then rationalize, this also becomes root 2 over 2. So your x coordinate is also 1 times root 2 over 2, which is just root 2 over 2. And then on our very last one, this one's actually kind of tricky in that it's so easy. You have a point 9 units from the origin in Q1. Well, 9 is your radius. So your equation, or your shortcut for your points, is r cosine r sine. So that's 9 cosine, 9 sine, and a is 9. So that's pretty straightforward. So because I'm remaking this video after class, something happened with the initial video I uploaded. I'm going to go through a couple of these examples with us, questions that I think some people had, and talk about them. And I'm going to start with number 1, where it says, which of the following statements is true for the given diagram? Well, a couple things without even reading these that we do know is true. Since this is 8, j is 8. So this is 8 cosine theta, 8 sine theta. We know j equals 8. If you look at your choices here, a lot of them contain, or a couple of them anyway, contain sine squared plus cosine squared. We just learned that that equals 1. So j times 1 equals 4 tells you j equals 4. Well, that's not true. On this one, cosine squared plus sine squared is 1. This tells you that j squared equals 8 squared, which is 64. So that would give you that j equals 8. So that's on my radar. This one's a little bit bizarre because it doesn't have the cosine squared and sine squared option. So I'm going to probably ditch that one. This one, this equals 1 based on our Pythagorean identity. And then you'd have 8j equals 1. It's really 8j times 1 equals 1, but I'm just putting 8j equals 1. Divide by 8 on both sides, and j equals 1/8, which is not true. So B is the answer here. You know, something like this. We have the sine squared of 2x and the cosine squared of 2x. But we've got this 1/2 in there. So actually, if you factor out that 1/2, and then you'll have sine squared of 2x plus cosine squared of 2x. Now this is just 1. Sine squared of something plus cosine squared of something is just 1. So you have a 1/2 times 1 equals 1. That's never true. Never ever true. No real values of x. Okay. This one's of a different nature. They give you cosine squared, ask you for cosine squared. So since the sine squared plus the cosine squared is supposed to equal 1, your sine squared is 0.2. You don't need to square it. That already is the sine squared value. If they had given you the sine value, then you'd have to square that. But they already are giving you the sine squared value. And then so you subtract 0.2 from both sides, and cosine squared, which is what they're asking for, is just 0.8. This is just our property. Sine squared plus cosine squared is 1. Up here, this is just our property. Sine squared of 2a plus cosine squared of 2a. As long as it's the same angle twice, it equals 1. This, again, is never going to be true because it's sine squared of an angle plus cosine squared of the same angle. So this is our identity. This always equals 1. So that'll give you 1 equals a half. Never true. So that pretty much covers all the types on your homework. That could, that should help you with, this one on the back, number 10, is very similar to number 1 that we looked at. And then this one is just a 0.1, very similar to what was on our notes. So I don't anticipate any trouble with 9, but number 10 maybe, but now that we've gone over number 1, hopefully you can take another look at that and understand it better. So that's all for now, and I hope to see you tomorrow.